Let's look at one more example where we will do a ray diagram and use the equations to verify our answer. This example, we have a diverging lens. We have an object placed 30 centimeters in front, and the problem is nice enough to remind us that the focal length is negative because it's diverging. But if it didn't give you that negative, you'd still need to put it in. And find the image, location, and magnification. So first thing we're going to do is we're going to draw the lens. I already have the vertical line here. Since it's diverging, I like to use this kind of notation for diverging, right? You can imagine that this was filled in like this and it looked like a diverging lens. And then the next thing we're going to do is draw our focal points on either side. So 10 centimeters focal length, I'm going to use one of these squares representing 10 centimeters. That's going to be the F on both sides. Next thing is to draw the object. So it says it's 30 centimeters in front, so it's going to be 3 of these squares here. And I happened to make it 4 squares high just because I knew that the image formed was going to be smaller, so I didn't want it to be too small. And now we are ready to draw our 3 rays. So the first ray, well actually let's go back and write this down here. So for the diverging lens, we have parallel and focal on the same side. Then it goes, the second ray goes to the center, and then it's focal parallel on the other side. So that helps us draw our rays. So our first ray is going to be parallel. So we're going to go ahead and originate it from the object. It's going to be parallel. Whoopsie, let's have a nice, there we go. But then as soon as it hits the lens, it's going to diverge as though it came from the focal point on the same side. So what we do is we're going to draw a line that appears to come from that focal point. You could have a dashed line here, and then you could see that it would have to have the same slope. You can count your squares, up 4 over 5, up 4, and over 5. So this line here has the exact same slope as though it's coming from that focal point. And then the second ray is going to go through the center and keep going. So start it right there and then have it go right through the center. We'll try to be as accurate as possible, and we could count squares if we wanted to. And then the third ray is going to try to go to the focal point on the other side, right over here. But as soon as it hits the lens, then it's going to refract parallel to the optical axis. So what we need to do here is draw a line that tries to go all the way here, so we know the slope of that line. So we can see that it's hitting the lens right here. As soon as it hits the lens, then we want to have it emerge parallel. So it's going to go off that way as soon as it hits the lens. So those are our 3 rays. And then what we need to do is we need to trace them back to see where they intersect to find our image. So usually I do this with a dashed line, but just kind of a rough estimate here. Just kind of follow the slope of your original line, and we're just tracing it back here this way, and then we're going to trace back the purple ray. The blue ray is already traced back. We don't have to worry about it too much. So you can see we trace back the purple one, and we can see that all 3 rays intersect right there. So we're going to put our image right there. It kind of looks like it's on this grid line, but it's a little bit to the right of it. Right there is our image. So you can see that with this ray diagram, we don't know exactly where is that image. So it's good to use the equations to get a more exact answer. We do know that the image is virtual and smaller than the object, but we don't know exactly where it is. So let's use the equations here. Let's define our f and our p. Focal length of a diverging lens always negative 10 in this case. And then the object distance is going to be 30 centimeters. So let's find our image distance q. When we use the thin lens equation, the 1 over p plus 1 over q equals 1 over f, just like in the previous problem. When we solve for q, we're going to get p times f divided by p minus f. Be careful with the negatives here. So we get 30 times a negative 10 divided by 30 minus a negative 10. So we get negative 300 over 40, which gives us negative 7.5 centimeters. So you can see that it wasn't exactly on this grid line here. It's negative because it's in front of the lens, it's a virtual image. And then we need to find the magnification. Magnification is going to be equal to negative q over p. So we're going to do negative times a negative 7.5 divided by positive 30. So we'll get a positive answer. We get 0.25. So we can see that the image is actually 1 square tall, while the object was 4 squares tall. So it's 1/4 of the size, which is why the magnification is 0.25. It's positive because the image is upright. So that's it for this video. The last video for this section, we are going to put more than one lens together.